Hello everyone, my name is Bruno Rodrigues and I will present the cooperative DDoS signaling based on a blockchain system, which is the outcome of my PhD thesis advised by Professor Burkhard-Stiller. The main motivation to think in cooperative defense is the growing number of DDoS attacks in the recent years. We can follow the chart on the right, which has, and it's mostly due to an increasing number of connected devices, IoT and non-IoT, and also the available bandwidth. One issue is that most of those devices, they are not secure, most of them IoT devices in this case, which makes them a target by botnets that exploit those devices to launch attacks. In this scenario, we have that, in scenario of large-scale DDoS attacks, we have that centralized systems, they are easily overloaded. In a situation that if you try to increase the hardware and software available there, it's not ideal because the attack is always more distributed than the capacity of the defense, and that's the main reason why the DDoS defense systems, they require a more coordination and also more distribution. That then you could reduce the burden of the detection and mitigation in a single domain, in a centralized system, and also extend the mitigation capabilities, because you can consider that different systems, they have different capabilities, different DDoS detection mechanisms. And one third point, for instance, is that you could reduce the burden of having less traffic traversing the internet infrastructure. In this scenario, we identified in the thesis 4 different scopes in which we can analyze cooperative defense systems. The first one is the technical basis, in which we are mostly dealing with heterogeneous networking systems, and that's one major point in which why it's difficult to have a cooperative system working. We have a lack of standards for protocols and operations to make those systems to communicate, and most existing systems, they have a high complexity of deployment and operation, which means that you need to change your current and existing networking devices, to change your network management system. That employs in high complexity to make such a cooperative defense system happens in real life. On a social basis, we have also problems that are no less important, that relates mostly with how you manage trust within an alliance. Why I should trust another system that could use, for instance, my potential downtime as a way to increase or decrease my public image. And it's very important to consider this social aspect within a cooperative defense system, which is how you manage trust within this alliance. A third point is related to the establishment or not of incentives. You have that requesting a cooperative defense to a third-party system involves incur in operational expenses, and those are often neglected, as we are going to see, and there is a need for incentives. And the fourth dimension is that mostly easily solvable on a technical basis, but very complex in real life, is that legal issues. You have different legislations across different regions, which impairs those systems to share information in practice. We identified in an analysis of the state of the art how those different systems since the year 2000 until 2020, how do they cope with those 4 different dimensions, and we can see here that most of them, they provide a solution that would reduce the burden on the underlying infrastructure. So we have more than half of the analyzed systems, and for 48% of them, they cope partially with this issue, which relates mostly to the first proposals of cooperative systems. All of them, they do not offer means in which you can share incentives, so another third-party system could use their resources, use their team to mitigate the service. And also an interesting point is that the social aspects, they are often not observed on those cooperative systems, which is the same from the legal aspect. And the goal inside this thesis and inside of the blockchain signaling system was to use an overlay network in which you can do the signaling, decoupling this network from the effective underlying mitigation service. So you have only a solution that could do the communication, and you have a solution that will try to cope with those challenges in 4 different dimensions. Let's see how. So the research questions, they are observable as a pyramid in which you have the technical layer as the basis in which you build or you try to address all the different challenges. And the social relates to trust and confidentiality, economical providing incentives, and legalist compliance across these different regions. The first one is how we can reduce complexities related to the operation and deployment. This is very important, so you want a wide usage of the cooperative system, and you don't want ideally impose less requirements on the infrastructure, and this is key to have a wide deployment. The second aspect is, especially talking about a blockchain-based system, is the need to balance for transparency and privacy. In one side, transparency helps to increase trust. On the other side, privacy relates to sharing only the amount of information that the other system that you are cooperating with should see. And third one relates to providing financial incentives, and fourth one in which you can tick off or tick in compliance aspects within a smart contract. In a quick overview, how the system works, we can imagine that we have a BLOS network, this alliance between those different autonomous systems, and each one of them has a decentralized application, the DApp of BLOS, that will communicate with the network. We can imagine that a given autonomous system is under large-scale DDoS attack, and this system will try to solve or to mitigate the attack on its own, and we would not be able to do it. What this system will do is to prepare an attack report containing target, actor, and mitigation, and different files, different fields. And in this field, it will be signaled to the systems that subscribe to that network, to those networks involved in the attack. We can imagine here that those systems will be involved. They will be, once the information is sent to the blockchain and this file is received by those different, this block is received by those different autonomous systems, and then they can react upon the signaling. In this situation, we can imagine that they accept, they mitigate the attack on their local networks, and then they are able to receive the incentive that is associated with that request. How this is implemented in practice, we prepared a system that is mostly based on the premises of software-defined networking and also virtual networking function. This is to provide a software-based, completely software-based approach that will react upon requests. And we can imagine that the system is deployed in a VM, and this will already simplify a lot the deployment and the operation of the system. We also have a component that's called Pollen that will encapsulate all the communication-related tasks with the Ethereum network, and also the stock, which will do the communication and the interface with network management system, and the database in which you can store all the policies and the configurations that are necessary. Along with that, we used the IPFS, the Interplanetary File System, with an encrypted channel. And why we use IPFS is because if you want to share large files of blacklisted addresses, for instance, those are not natively within the blockchain. So only a pointer is shared to the file in the blockchain, and the file goes on this off-chain network based on IPFS. We also have a model to deal or to handle reputation and reward aspects that would communicate with the polling database. This is how the system is implemented, those different models are implemented in practice. And this is the key part on the design of the thesis, is how the target and the mitigator, how they interact with. So this was done by defining a protocol that was implemented by a smart contract on-chain that would regulate how the decentralized app can interact with target and the mitigator, and vice versa. We have mapping of all those different outcomes, and also we can see that on the left, the target would initiate a request by signaling one attack. The mitigator would then approve. The target would need to send funds, and the protocol, the iteration happens, and so on. Important is to include a mutual evaluation of the service, which means that the target will evaluate the service provided by the mitigator. Once the mitigator uploads a proof of mitigation, which can be based on log files, which can be verified whether the incoming traffic from that mitigator was reduced or not. And then the target will do a first evaluation of the mitigator. In the second step, the mitigator would also evaluate the cooperation with the target. So we have this mutual evaluation. And related with the providing incentives in this collaboration, we have that economic aspects are handled by, once a mitigator approves a service, the target will need to send the incentives that are associated with the service provided by the mitigator. That is, the mitigator will define the amount that is required to provide the service. Those funds are locked within the contract, and it's only released in case of a positive outcome, which we are trying to map here in the protocol all the possible behaviors. So we have irrational behaviors in which someone do a service and the other party either do not cooperate or provide a rating that makes no logic, irrational. And the positive outcomes are mapped in green. Situation that we have a conflict is mapped in 9. So in case that one provide a service, the other denies, provides a bad rating for the service, and it's natural for the mitigator to complain. So there's a situation that escalates and need to be solved by a third party. And this is the design of how two instances they should cooperate with each other within the system. And this was evaluated in different dimensions across the PhD, in which we are going to quickly outline here a few and focus on the ones in blue. The first part of the system was to evaluate the functionalities and correctness, and this was done mostly in 2 stages. The first stage was to start the first year of the thesis building an emulation system based on Mininet and Truffle. In the second part, we scaled to the cluster that you are able to see in the figure. So this cluster has 18 nodes and also used an SDN switches, Zodiac FX switches on top, and it implements a private Ethereum network, a permissioned. The goal there was to observe how the smart contract behaves, to fix all possible bugs and correctness, so we can have a system that is ready to scale to a worldwide scale. Also, the system implemented a dashboard in which you could easily, in a way that is more straightforward to the operator, to configure what is the target, to generate alarms, and to request or reject requests in case you are a target and you want to request cooperative mitigation. If you are playing the role of a mitigator, you could receive incoming requests that are signaled in this contract, and you can react upon by accepting or denying. We will focus in the next slide on those evaluations that were the worldwide ones, and also the smart contract vulnerabilities were analyzed in the thesis, which were not yet published. Concerning the reputation, the analysis of reputation, we used a beta reputation that would map the probability of binary events. And in this case, we have mapping as alpha as a positive and beta as a negative, and you could evaluate at a point in time the evaluation of a player, mitigator, or target by considering the relation between positive and negative relations. In the case, the more negative evaluations you have, the less closer to 1 is your rating. So therefore, the rating is from 0 to 1, and more negative reduces your reputation, so to say. We summarize here the interactions. So we have, if I'm not mistaken, 20 evaluations of 20 interactions across those different outcomes of the protocol, and we have that rational mitigator and the selfish mitigator, they were able to be rewarded. That means if you do mostly the rational, in which provides the service that was requested by the target, and this represents the point of view of the target that is evaluating a service provided by the mitigator. And we could see that the lazy mitigator, over time, he is being punished by just not providing an upload of the proof, or just not reacting upon the request from the target. Considering a different perspective, we have the mitigator evaluating the target, and similarly, the satisfied target had a most positive feedback from the mitigator, and the ones that are dissatisfied and also the selfish and uncooperative always remains the same. But mostly the protocol was able to punish the dissatisfied targets and also the selfish ones, that are ones that do not provide a feedback for the mitigator. Considering the latency from the protocol, another important aspect, because if you want to see whether the system is usable in real life or not, and this evaluated the scope, was important to see how much time it takes to the protocol to reach and end the final outcome. We deployed 4 instances for that in Zurich, São Paulo, Ohio, and Tokyo, in which we evaluated every scenario of the system, also 20 runs for each end scenario using a script, in which a worst case scenario we had what's the step number 7, and mostly the step number 7 because it has more interactions between the target and the mitigator. And at the end, it made sense that this step, the scenario number 7, in which you have a situation in which the target is selfish and do not react upon the upload of proof, and also the mitigator is selfish. In this scenario, we had almost 2 minutes of execution here, which in the worst case scenario we can analyze here that, for instance, in 2018, the average attack duration was 218 minutes. So having 2 minutes of, in the worst case scenario, to converge to an end, to a final scenario of the protocol, it is an acceptable result in terms of performance. The last aspect that we analyzed is the off-chain signaling latency. We mentioned that we are using IPFS to do to exchange large list of IP addresses, and in this case we used a network that represents the same network of the BLOS, the blockchain signaling system. So the same instances that are in BLOS, they were also using IPFS, and also IPFS was able to provide a better latency, better response time considering to a centralized version, because the list of file was spread, was distributed across the network, and the victim and the mitigator, was able to retrieve faster from a closer source. And this is a clear architectural difference that provides a more faster response to IPFS in contrast to a traditional HTTP based request. In conclusion, here we have that simplicity is a key for wide applicability. So PLOS was designed with that in mind, in a way that you can combine with different protection systems and only be used in case of large-scale DDoS attacks where you cannot cope with the attack on your premises. And one important key aspect that is realized during the performance is that the cooperation do not need to happen in real time, but near real time, and which means that it does not need to react upon seconds, but within minutes. Hours is also not ideal. And performance has a secondary role in comparison with trust. Trust is one of the most, if not the most important aspect within the cooperation, and blockchain in this role is very useful to foster trust where there is already a pre-existing trust. So by only using a blockchain-based approach, it's not possible to make those systems that are not trusted to trust each other. Financial incentives are often neglected, and also legal issues, they are relatively solvable on a technical basis by detailing which system you can configure. On a future research, we have that the system could benefit from a dedicated blockchain-based structure, including side channels such as a PFS. Interoperability between different networks also is something that is highly desirable, and also deployment on a real scenario. That's it. Thank you. I'm open for questions.